Thank you very much for the introduction and for hosting this event and having me as a speaker. Do you see the presentation now full screen?
Yes, perfect.
Okay, okay, great. So, well, I don't have an outline slide, so I will just explain the title instead to give the outline. So the first thing I'm going to talk about is spacetimes with continuous metrics. What do I mean exactly, and what is the motivation for looking at that? Then I'm going to review causality theory briefly in the standard smooth case and also in the continuous case. And then in the end, revisit it. So I'm going to propose a new approach, and I'm going to explain what are the differences and what do we learn from that. So first, well, by a C0 spacetime, I will mean a C1 manifold with a C0 Lorentzian metric, so continuous metric, and a choice of time orientation. And then why do we care about this? So one motivation comes from the strong cosmic censorship conjecture, which in its modern form is essentially the question of whether certain smooth spacetimes can be embedded into a larger C0 spacetime. Another motivation are weak solutions to Einstein's equation. So if we want to model some phenomenon with the energy momentum tensor that is not smooth, is for example just continuous, then of course the solution will be also of a lower regularity. And lastly, more than a motivation to look at C0 spacetimes, just the kind of the approach I will take goes in the direction of axiomatizing causality theory, which is something that various authors have worked on for different reasons, just for mathematical reasons, but also this is motivated by quantum gravity, and also it is motivated by the desire to have a framework where C0 spacetimes, smooth spacetimes, different regularity classes can be understood. Okay, so first I briefly recall the causal relations on the spacetime. So the causal futures J plus are given by the pairs of points that are connected by a causal or non-space-like curve, and the chronological futures I plus, the same but for time-like curves. And then an important result in causality theory relating these two concepts is the push-up lemma, which tells you that if Q is in the causal future of P, then the chronological futures of Q and P are related by these two inclusions. So in the pictures, I show the future version. So this on the left would be the trivial case, and on the right would be the not so trivial case when P and Q are connected by a null curve. This is Minkowski, and the futures are included as here. And well, the curves I drew, they should motivate the name push-up lemma. Okay, but now what happens? So this lemma holds on smooth spacetimes. So what happens on continuous spacetimes? Well, it fails. This was shown by Fuchel and Grant in their 2012 paper, and the picture explains a bit why. So to understand this picture, it is easy. This can happen in any dimension, but in 2D it's easier to understand because in 2D, usually in the smooth case, the boundary of I plus can be found by just finding the two null geodesics, future directed, that start at P in the two possible directions. And you don't need to solve the geodesic equation. You just need the equation that the tangent vector is null. And now the initial value problem of null tangent vector starting, the curve starts at P and in this direction, for example, to the left. If the metric is smooth, it has a unique solution. But if the metric is only continuous, then it has solutions, but they're non-unique in general. And because of this, well, we have a whole family of null curves that start at P and go to the right, for example. And they span this whole blue region that will then be included in the causal future J, but not in the time-like future I. And this region in the paper it's called the causal bubble. And if we choose a point in the causal bubble, then obviously for the pair PQ, the push-up lemma fails because there is this red region which is in I plus of Q, but it's not in I plus of P, even though P and Q are causally related. Okay, and now, well, what could we do about it? So Sorkin and Woolgar already in 1996 proposed that maybe for continuous spacetimes, instead of having J plus, we should define a different notion of causal relation. And they made a proposal which is called Kplus, but I'm not going to explain it because I'm going to make a different proposal, which sort of in analogy to theirs, I call it lowercase k instead of uppercase k. And it's defined like this. So 2 points being Q, I say that Q is in the K future of P if these two inclusions hold between the chronological futures. And now this has the consequence that the push-up lemma it holds by definition. That these two inclusions are precisely the statement of the push-up lemma, and now I have them, they hold by definition. And moreover, this K plus is the maximal relation with this property. So any relation that is bigger than little k plus will not satisfy the push-up lemma, because by being bigger, it will include some pair of points where one of these inclusions fails. Okay? And now the first result, just a quick theorem, not very deep, is that this relation, it is transitive, reflexive, and it is contained in the closure, topological closure of I plus. And well, this is kind of a reality check. Like we want these properties to hold, to have something reasonable that we can call a causal relation. And now I will give some concrete examples to illustrate this. So in two-dimensional Minkowski space, we remove a point, and then we consider these 2 points PQ, which were joined by a null curve before, but now this null geodetic is cut out because I removed the point in the middle. However, the chronological futures are unaffected, and there's still the relevant inclusions hold. Therefore, P and Q in this picture, they are K-related, even though they are not J-related, so not in the usual sense. And now, what happens if instead of removing a point, I remove a line? Then the situation is different, because to the future, nothing has changed, but in the past, now the chronological paths of P and Q are disjoint, because I removed this line. So now P and Q are not K-related, because both inclusions would have to hold for them to be K-related. Nonetheless, Q is still in the closure of I plus of P. So we see here that the K relation is in general smaller than the closure. Okay? And now, well, this definition was just set theoretic, so can we still talk about causal curves? Is the next question, and the answer is yes. We can define them in the following way. So if you just look at this equation and the picture, what I'm saying is that for two consecutive points on the curve, what I'm asking is that the second one is included in the K future of the first point. Okay, and this has to hold for all pairs of consecutive points on the curve, which should be a continuous curve. And moreover, I want this to hold in a local sense, so that's why I'm talking here about neighborhoods, because otherwise I could have some kind of, let's say, interference of global effects. So for example, in some more pathological spacetime, it could be that globally the K plus relation is everything, and then every curve is K plus causal, and I don't want that. So I consider it locally, and in particular, K plus sub U means K plus defined on the spacetime U on this neighborhood. Okay? And this definition, the same, but with its standard J, was already given, for example, in the classical book by Hawking and Ellis. And now we can use this to define another relation that I call K twiddle. So the twiddle kind of represents a little curve. That's the idea, because this relation is simply defined by taking those points which can be joined by a K plus causal curve. And here comes the next theorem. So on smooth spacetimes, this K twiddle coincides with the usual J. And this is important because this means that K plus twiddle is a valid generalization of the usual causal structure to the case of continuous spacetimes. Because in the usual case of smooth spacetimes, it coincides with the usual notion. And now, since we are talking about causal curves, we can wonder about the limit curve theorem, which is another important result in causality theory. So using the standard notion of causal curves, the one defined by the metric, the one that gives G, even when the metric is continuous, we still have a limit curve theorem. The fact that it still holds in the C0 setting was also shown in the same paper by García and Grant. And this, well, let's say baby version of the limit curves theorem is the following statement. So we have a sequence of G causal curves, so causal curves in the usual sense defined by the metric. And this sequence uniformly converges against the limit curve gamma infinity. And the statement of the theorem is that gamma infinity is also a G causal curve. So the obvious question is, does the same hold for Kplus causal curves? And unfortunately, the answer is no. At least, I mean, in the case of smooth spacetimes, yes, which is not surprising because I showed before that the relation coincides with J plus in the smooth case, but in the interesting case, which is continuous spacetimes, we don't have a limit curve theorem. And I'm going to give a rough idea why we don't have a limit curve theorem. And it's the following. So essentially, we have this limit curve, gamma infinity, and we want to consider a neighborhood. And then we consider two consecutive points on the limit curve. And we see them as limits of a pair of points on the sequence. Now, if the relation K plus is closed in the neighborhood, in the sense that this set here is a closed set, so the set of points in the product U times U which are related, then obviously gamma infinity is going to be a K plus causal curve because these 2 points lie in the closure of this set. And if K plus includes this closure, then everything is fine. But it turns out we have examples where this does not hold, the set is not closed. And in fact, we also have specific examples of sequences of curves which converge against a curve that is not causal. Even sequences of time-like curves that converge against a curve that is not causal. And this lets us draw a deeper conclusion, even because recall that K plus was the maximal relation such that the push-up lemma holds. So any relation bigger than K plus does not allow for a push-up lemma. However, we see here from this rough explanation that what we would need in order to have the limit curve theorem is to add more points. We would need to add the limit points. But if we do that, then we lose the push-up. So the conclusion is that both at the same time is not possible. And this, well, here I just gave a rough explanation, but in the paper, this point is made more precise. Yeah, and now I'm going to conclude the talk by briefly summarizing. So what have we done? The first thing we have done is we have developed a set theoretical way to construct the causal relation out of the chronological relation. And in particular, the manifold structure and the metric was only used implicitly in the definition of I plus, but other than that, we didn't use it. So in principle, if I give you a set and I give you a relation that I decide to call it the chronological relation, then one can construct the causal relation K plus out of that. So it's applicable in a very broad context. Furthermore, we have applied it specifically in the case of C0 spacetimes, and that has given us a causal structure that satisfies a push-up lemma, which is not the case with the standard causal structure. But we've paid the price of losing the limit curve theorems instead. So it was a trade-off. But as I just said, this is unavoidable. So what is shown in the paper is that if you take the I plus given in the usual way by causal curves, and the metric is only continuous, then there does not exist any relation playing the role of causal relation that would satisfy both the push-up lemma and the limit curve theorem. And furthermore, in fact, in the paper, it's also considered the case of keeping J plus given and then trying to find the suitable I plus. And also that doesn't work. Also then one has to sacrifice one important property. Okay, and this concludes my talk. So thank you very much for your attention. And here's the archive identifier in case you're interested.
Okay, thank you very much for the interesting talk. and also for staying perfectly in time. And I see we already have a question. So Claudio Baccanini.
So thanks for this very interesting talk.
Sorry, it's very low, so you have to maybe repeat the question.
Okay, so thanks for this very interesting talk. It's like this set theoretical definition is very interesting. It's something maybe that would be interesting to look at in the context of the causal fermion systems framework, because there you have sort of this problem where you have local causal relations, but there's no proper formulation of sort of like global causal structures yet. And yeah, it's a problem I've been thinking about before, and I think this work, what you've been doing here, might be applicable to that setting. So that's more sort of a comment.
Okay, thank you very much for that comment. I never thought about that, so I don't know much about causal fermion sets, but thank you. I hope it might work. Otherwise, the capital K plus of Sorkin and Volkar might also be an option. Maybe you also want to check that.
Okay. Further comment?
May I make a comment and a suggestion? So the first comment is that this last point on your slide is a very nice result. So I like this a lot. If you want to do causality theory, you need both the push-up lemma and the limit curve. And so that's the two tools that you have, and you can prove things with that. And if you're missing one, then you're just essentially, it's a, and you can do much less. So that's a very nice result. And second comment now, so one of the key things which one uses in causality theory is the notion of generators of horizons. And I've struggled quite a bit of trying to understand how to formulate this and get any result in this spirit. And maybe your Kplus relation could be useful to define generators of horizons or something like that in for continuous metrics. So I don't know if you ever thought about this, or if not, maybe that would be an interesting thing to do.
Okay, thanks for your comment. I have not thought about that either, but well, I'm very happy to see that there is a potential for application. And I agree with your previous point that really both the push-up and the limit curve theorem, and in fact also the openness of the chronological relation. I think those three are like the key tools. With those three, you can do all of causality theory basically, but if one fails, then it's pretty bad.
Okay, further questions or comments?
I would like to ask a simple question. Maybe the notion C0 space-time is misleading, because it does not mean that the manifold is C0, yes? So this is just C0 with respect to the metric tensor, yeah? This is the idea. But what is the underlying structure of the manifold itself? Is it only differentiable or smooth or whatever? What kind of atlas we use on a manifold?
C infinity.
Yeah. Thank you. I use a C1 atlas. So in principle, the natural thing to do is to have the metric to be CK and then the atlas to be CK plus 1. Because
only.
For example,
only. Mm-hmm.
Only. I mean, but however, there's a theorem that says that any C1 atlas has a C infinity sub-atlas.
Yeah, exactly.
So you could do that, but I think that if you choose a C infinity sub-atlas, you're making a choice that I don't want to make a choice, because maybe
it depends but it depends on the application. If you want to analyze the shells, for instance, it's easier to work with smooth atlas and and distributions, you know, just.
Yes.
So it depends on the applications.
Otherwise, you don't have a concept of test function space. I mean, so.
Yeah, exactly. So.
Okay. Further questions or comments? Well, if not, then let's thank the speaker again. Thank you very much for the nice presentation.